Hello and welcome. Tonight, we are going on a quiet journey through one of the largest questions the human mind has ever asked. How big is the universe? It sounds like a simple question at first. We ask how wide a room is, how far away a mountain stands, how deep an ocean reaches, or how many kilometers separate one city from another. We measure things, place numbers beside them, and imagine that if we had a large enough ruler, a powerful enough telescope, or a long enough journey, we could measure anything. But the universe is not like a room. It is not an object sitting inside something larger, waiting for us to walk around it and find its edge. It is space itself, stretching in every direction, carrying galaxies, stars, planets, light, dust, radiation, dark matter, and the silent expansion of time. In this video, we will slowly explore the size of the universe, from the world beneath our feet to the farthest light we can see. We will travel beyond Earth, beyond the moon, beyond the planets, beyond the Milky Way, beyond galaxy clusters, and out toward the edge of the observable universe. And there, at the edge of what we can see, we will find not a wall, not a border, not the end of existence, but a horizon. A limit created by time, light, and cosmic expansion. So settle in, breathe slowly, and let the scale of the universe open gently around you. Begin here. With Earth, our home, a planet about 12,700 kilometers wide, wrapped in air, clouds, oceans, forests, deserts, ice, cities, and night. From the ground, Earth can feel endless. A child looking across a field may feel that the world goes on forever. A traveler crossing an ocean may feel that the planet is unimaginably vast. Mountains rise like walls. Storm systems stretch across nations. Deserts can take days to cross. Even a single forest can seem like its own universe. But from space, Earth becomes small, a blue sphere. A bright bead in darkness. The atmosphere, which feels so wide when we breathe it, becomes a thin, glowing skin. The oceans become smooth, patches of blue. Continents become shapes. Clouds become swirls. The whole human story becomes wrapped around one small world, turning quietly in sunlight. The moon is our nearest large companion. It orbits Earth at an average distance of about 384,000 kilometers. That is far enough that every planet in the solar system could fit between Earth and the moon if placed side by side. Yet in cosmic terms, this distance is tiny. Light, traveling at about 300,000 kilometers per second, crosses the distance from the moon to Earth in a little more than 1 second. 1 second of light travel, that is our first step into cosmic scale. Light from the sun takes much longer. The sun is about 150 million kilometers from Earth. Its light takes just over 8 minutes to reach us. When sunlight touches your window in the morning, it has already been traveling through space for more than 8 minutes. The warmth on your face is not quite from the sun as it is now, but from the sun as it was a few minutes ago. This is one of the first strange lessons of distance. To look far away is to look back in time. The moon is about 1 light second away. The sun is about 8 light minutes away. The outer planets are light hours away. Neptune, the farthest major planet from the sun, is so distant that sunlight reaching it is faint compared with the light Earth receives. Out there, the sun is still the brightest star, but it no longer rules the sky in the same warm way. It is smaller, colder looking, more distant, like a memory of fire. And still, Neptune is only inside our solar system. The solar system itself extends far beyond the planets. There are icy bodies in the Kuiper Belt, where Pluto and many other small worlds travel in long, cold orbits. Beyond that, there may be a vast, distant shell of icy objects called the Oort cloud, so far from the sun that its outer regions may reach a large fraction of the way to the nearest stars. Already, the size is difficult to hold in the mind. but the solar system is only one small neighborhood around one ordinary star. The nearest star system to the Sun is Alpha Centauri, a little over 4 light-years away. That means the light we see from it tonight began its journey more than 4 years ago. If a message could travel at the speed of light, which is the fastest speed information can travel according to our understanding of physics, it would still take more than 4 years to get there and more than 4 years for a reply to return. A conversation with the nearest stars would take almost a decade for one exchange. And that is only the nearest system. Our galaxy, the Milky Way, contains hundreds of billions of stars. It is a vast rotating island of starlight, gas, dust, dark matter, and old stellar remains. Its bright disk is roughly 100,000 light-years across, though its surrounding halo and dark matter structure reach even farther, 100,000 light-years. If you could travel at the speed of light, which no spacecraft with mass can do, it would still take about 100,000 years to cross the bright disk of the Milky Way. Human civilization, written history, mountains of language, empires, discoveries, songs, wars, dreams, and generations all fit into a time far shorter than a beam of light would need to cross our galaxy. The Milky Way is not empty. It is full of stars. Some are bright blue giants that live fast and die young. Some are red dwarfs that may shine for trillions of years. Some are white dwarfs, the cooling remains of stars like the Sun. Some are neutron stars, crushed remnants so dense that a spoonful would weigh more than a mountain. Some are black holes, dark collapsed objects where gravity bends space-time so strongly that light cannot escape from within the event horizon. Between the stars are clouds of gas and dust, some cold and dark, some glowing with the light of newborn stars. There are nebulae where stars are born, planetary systems still forming, dead stars fading, and planets traveling unseen around distant suns. Our Sun is one star among many, not at the center, not at the edge. Simply one star in the galaxy's disk, orbiting the galactic center once every couple 100 million years. Since the Sun was born, it has circled the Milky Way many times, carrying Earth, the Moon, and all the planets with it. From Earth, the Milky Way appears as a pale band across the night sky, if the night is dark enough and far from city lights. That band is not a cloud in Earth's atmosphere. It is the combined glow of stars too numerous and distant for the unaided eye to separate. When we look at it, we are looking through the disk of our own galaxy. We are inside the thing we are trying to understand. That alone makes the scale difficult. Imagine a single grain of dust trying to understand the shape of the whole desert, and yet, through telescopes, mathematics, and patient observation, we have learned that the Milky Way is only one galaxy among many. The nearest large galaxy to ours is Andromeda, about 2.5 million light-years away. When we see Andromeda in the night sky, we see it as it was about 2.5 million years ago, before modern humans had appeared on Earth in the form we know today. Its light began crossing intergalactic space while ancient human relatives walked beneath unfamiliar skies. Andromeda is moving toward the Milky Way. In several billion years, the two galaxies will likely merge into a larger galaxy. But on the scale of galaxies, even collision does not mean what it means on Earth. Stars are so far apart that direct stellar collisions would be rare. Galaxies pass through and around each other like vast ghostly cities, their gravity reshaping disks, streams, and orbits over hundreds of millions of years. The Milky Way and Andromeda belong to a small collection of galaxies called the Local Group. It contains several dozen known galaxies, many of them small dwarf galaxies, orbiting the larger ones. The Milky Way, Andromeda, and the Triangulum Galaxy are among its main members. The Local Group is about 10 million light-years across. Already, the numbers have grown from seconds of light to minutes, hours, years, thousands of years, millions of years. But the Local Group is still only a tiny part of something larger. Galaxies gather into groups. groups gather into clusters. Clusters connect into filaments. Filaments surround enormous voids. Together, they form the cosmic web, the large-scale structure of the universe. On the largest scales we can map. Galaxies are not scattered evenly like dust on a table. They form a vast web-like pattern. Long threads of galaxies and dark matter stretch across hundreds of millions of light-years. Dense knots form where clusters gather. Between them lie great voids, regions of space that are not truly empty, but contain far fewer galaxies than the cosmic average. The universe is not a simple fog of stars. It is structured. It has texture. It has rivers and walls and empty regions, all shaped by gravity, dark matter, expansion, and the tiny early fluctuations that were present when the universe was young. Our local group belongs to a wider region associated with the Virgo supercluster and the even larger Laniakea supercluster, a vast flow of galaxies moving through the cosmic web. But even these structures, enormous as they are not the universe itself. They are only patterns within the observable universe, one level in a hierarchy of scale. To measure the size of the universe, we must go beyond galaxies. We must go beyond the structures that gravity has built. We must ask how far light has been able to travel since the beginning of cosmic history. The universe is about 13.8 billion years old. This number can be misunderstood. If the universe is 13.8 billion years old, one might guess that the observable universe should be 13.8 billion light-years in radius, or 27.6 billion light-years across. After all, light travels 1 light-year in 1 year. So if light has had 13.8 billion years to travel, should the farthest light not be 13.8 billion light-years away? It seems reasonable, but the universe has been expanding while the light has been traveling. Space itself has stretched. A photon from the early universe may have traveled for nearly 13.8 billion years, but the matter that released that light is now much farther away than 13.8 billion light-years. The distance today to the edge of the observable universe is roughly 47 billion light-years in every direction. That makes the observable universe about 94 billion light-years across. This does not mean light traveled faster than light. It means the space between us and the source expanded during the journey. There is no violation in that. In general relativity, galaxies far enough away can recede from us faster than light because of the expansion of space itself. They are not flying through space faster than a light beam passing them locally. Rather, the space between distant regions is growing. This is one of the deepest differences between motion through space and expansion of space. A galaxy can be carried away by expanding space so quickly that its distance from us increases faster than light could cross that distance, while locally nothing breaks the speed limit. The observable universe, then, is not the whole universe. It is the part from which light has had time to reach us. It is our cosmic horizon. Beyond it, there may be more galaxies, more clusters, more voids, more dark matter, more light that has not reached us and may never reach us. The universe does not necessarily end at the edge of what we can observe. The edge is an observational limit, not a wall. This may be the most important idea in the whole journey. The observable universe has a size. The whole universe may not have a known size. It may be finite. It may be infinite. If it is finite, it may be far larger than the observable part. It may have a shape or topology that wraps around in ways difficult to picture, so that traveling far enough in one direction might, in principle, return you to where you began, though no such wrapping has been observed on the scales we can see. If it is infinite, then there is no final edge at all. Space continues without limit, containing regions forever beyond observation. We do not know which is true. Observations suggest that the universe is very close to spatially flat on large scales. But flatness does not automatically tell us whether the universe is infinite. A flat surface can be infinite like an endless plane, or finite in a more complicated shape that loops back on itself. The same general idea can apply to space in more dimensions. So, when we say the universe is about 94 billion light-years across, we must be careful. That is the observable universe. Not necessarily everything. Everything may be much larger, perhaps endlessly larger. Our cosmic horizon is like the horizon at sea. Standing on a ship, you can see only so far because Earth curves away from you. The ocean does not end at the horizon. It continues beyond what your eyes can reach. In the same way, the observable universe ends at a horizon created by the finite age of the universe, the speed of light, and cosmic expansion. Beyond that horizon may lie more universe, possibly much more, possibly infinitely more. The farthest light we can see is not from stars or galaxies. It is the cosmic microwave background, the afterglow of the hot early universe. It comes from a time about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and nuclei to combine into atoms. Before that, space was filled with a hot plasma that scattered light again and again. The universe was not transparent in the way it is now. When atoms formed, light could finally travel freely. That ancient light still fills the sky today, stretched by the expansion of the universe into microwaves. It is faint and cold now, only a few degrees above absolute zero, but it carries a picture of the early universe. Tiny temperature variations in it reveal the seeds of future structure, the slight differences in density that gravity would later grow into galaxies and clusters. In every direction, we see this ancient glow. It surrounds us not because we are at the center of the universe, but because wherever an observer lives, their observable universe is centered on them. An alien astronomer in a galaxy billions of light-years away would see their own cosmic microwave background surrounding them with their own observable horizon. Every observer has a sphere of what can be seen, defined by the light that has reached them. This can feel strange. It may seem as though Earth is at the center, but it is not. We are at the center of our observable universe only in the same way you are at the center of your visual horizon when you stand in a field. The horizon surrounds you because you are the observer, not because the entire world is centered on you. The universe has no known central point. The Big Bang was not an explosion from one point into empty space. It was an expansion of space itself. Every distant galaxy, on average, sees other distant galaxies moving away. The expansion is not from a special center. It is everywhere. A simple image helps, though it is imperfect. Imagine dots on the surface of a balloon as the balloon inflates. Each dot sees the other dots moving away. No dot on the surface is the center of the expansion on the surface itself. The surface stretches everywhere. In a similar way, space expands and distant galaxies become farther apart. But the balloon image has limits. The universe is not simply the surface of a balloon floating inside a larger room. It does not need an outside space in the ordinary sense. The image only helps us see how expansion can happen everywhere without a center on the surface. The true universe is not easy to picture. That is part of its beauty. The scale of the observable universe is so large that ordinary comparisons begin to fail. A human body is measured in meters. Earth is measured in thousands of kilometers. The solar system is measured in astronomical units, light minutes, and light hours. Nearby stars are measured in light years. The Milky Way is measured in tens of thousands of light years. The distance to nearby galaxies is measured in millions of light years. Galaxy clusters and cosmic filaments are measured in tens or hundreds of millions of light years. The observable universe is measured in tens of billions of light years. Each step is not merely larger. It is a change in the kind of imagination required. To cross Earth at the speed of a jet plane takes hours. To reach the moon with a spacecraft takes days. To reach Mars can take months. To reach the outer planets takes years. To reach the nearest star with current spacecraft would take tens of thousands of years. To cross the Milky Way at the speed of light would take 100,000 years. To reach Andromeda at the speed of light would take 2.5 million years. To cross the observable universe at the speed of light, if the universe were not expanding, and if such a journey made sense, would take tens of billions of years. But the universe is expanding, and the expansion changes the meaning of travel itself. There are galaxies whose light reaches us today, but which are now so far away and receding so quickly because of cosmic expansion that light emitted by them today may never reach us. We see them as they were long ago, but their present has moved beyond our future visibility. This is one of the loneliest facts in cosmology. The universe is not only vast, parts of it are disappearing from possible contact. As dark energy drives the accelerated expansion of the universe, distant galaxies outside our gravitationally bound neighborhood will become harder and harder to see. Over immense time, their light will grow redder, fainter, and more stretched. Future astronomers in our galaxy, billions or trillions of years from now, may see a much emptier sky beyond the local group of merged galaxies. The universe we see now is a temporary gift. The distant galaxies are visible because we live at a time when their ancient light can still reach us. In the far future, much of the cosmic evidence we use today may fade beyond detection. This makes our moment special, but not central. We are not at the center of space. We are not at the center of time. But we live in an era when the universe is old enough to contain galaxies, stars, planets, and minds, yet young enough that the deep cosmic past is still visible. The size of the universe is therefore also a story about timing. If life had appeared much earlier, there would have been fewer heavy elements, fewer stable planets, fewer mature galaxies. If life appears much later, the distant universe may be hidden by accelerating expansion. We are here in a middle age of cosmic visibility, looking out while the great evidence is still written across the sky. When we look far enough, we see galaxies as they were when young. With the most powerful telescopes, astronomers can observe galaxies whose light began traveling when the universe was only a small fraction of its current age. These galaxies appear faint, redshifted, and small. Their light has been stretched by expansion. Their shapes and stars tell us about the early stages of cosmic history. Redshift is one of the main tools for measuring cosmic distance. As the universe expands, light traveling through space is stretched to longer wavelengths. Visible light can become redder. Ultraviolet light can stretch into visible or infrared. The more the universe has expanded during the light's journey, the larger the redshift. By measuring redshift, astronomers can estimate how far away a galaxy is and how long its light has been traveling. This is how distance and time become connected in cosmology. A faraway galaxy is not only far away in space, it is far away in time. We see it as it was. The deeper we look, the younger the universe becomes. At the farthest visible limit, we do not see galaxies at all. We see the cosmic microwave background, the baby picture of the universe, before stars and galaxies had formed. Beyond that, light cannot show us directly, because the earlier universe was opaque to light. To study earlier times, scientists use theory, particle physics, cosmic background patterns, gravitational waves, if they can be detected from early eras, and other indirect clues. The observable universe is therefore layered. Nearby space shows us the recent universe. Distant galaxies show us the young universe. The cosmic microwave background shows us the universe when it was about 380,000 years old. Beyond that lies an even earlier universe hidden from direct light. and beyond our horizon lies space whose light has not reached us. The size of the universe is not just a number, it is a structure of visibility, a sphere of time around every observer. The observable universe contains an extraordinary amount of matter and energy, though most of it is not the ordinary matter we see. Current estimates suggest that only about 5% of the universe is normal matter, the kind that makes stars, planets, gas, dust, and bodies. About 27% is dark matter, a form of matter that does not emit or absorb light in the usual way, but reveals itself through gravity. About 68% is dark energy, the mysterious component associated with the accelerated expansion of the universe. This means that almost everything in the universe is hidden from direct sight. The stars, galaxies, nebulae, planets, and glowing gas that fill our images of space are made from the small visible fraction. The universe we see is not the whole inventory. Even within the observable universe, most of what exists is dark. Dark matter helps shape galaxies and clusters. Without it, galaxies would not rotate as they do, clusters would not hold together as observed, and the cosmic web would not have formed in the same way. Dark energy, even more mysterious, appears to dominate the universe's expansion at large scales, pushing the cosmos into accelerated growth. So when we ask how big the universe is, we are also asking about something mostly invisible. We measure its size not by walking across it, but by reading light, gravity, temperature patterns, redshifts, galaxy distributions, and the expansion history of space. The universe is measured through traces, through photons arriving after billions of years, through the bending of light by gravity, through the motions of galaxies, through faint microwaves from the early cosmos, through the way clusters gather and voids open, through the silence between the stars. The number 94 billion light-years is enormous, but even it may be only the beginning. If cosmic inflation occurred, as many models suggest, then the whole universe could be vastly larger than the observable universe. Inflation is the idea that in an extremely early moment, the universe expanded extraordinarily rapidly. It helps explain why the universe appears so smooth and flat on large scales, and why regions far apart have similar properties. But inflation also suggests that the part we can observe may be only a tiny patch of a much larger whole. How much larger? We do not know. Some versions of inflation allow the full universe to be unimaginably larger than the observable universe. Some even suggest an eternal process producing regions beyond our horizon. These ideas are fascinating, but they must be spoken of carefully. The observable universe is measured. The much larger whole is inferred through models and remains beyond direct observation. This boundary between knowledge and possibility is important. A good documentary about the size of the universe should not pretend we know what we do not know. We know the age of the observable universe with impressive precision. We know the approximate size of the observable universe. We know the universe is expanding. We know distant galaxies show redshift. We know the cosmic microwave background fills the sky. We know normal matter is only a small fraction of the cosmic contents. We know the large-scale structure forms a cosmic web. But we do not know the total size of the entire universe. We do not know whether it is finite or infinite. We do not know its full topology. We do not know whether regions beyond our horizon are exactly like our region or different in ways we cannot measure. We do not know whether the observable universe is a tiny patch of something unimaginably larger or simply one horizon within an endless space. The honest answer to the question, how big is the universe, has two parts. The observable universe is about 94 billion light-years across. The entire universe may be much larger, and its true size is unknown. That answer may feel incomplete. But it is more beautiful than false certainty, because it means the universe is both measured and mysterious. Known enough to map, unknown enough to humble us. Imagine now that we could rise far above the Milky Way. The galaxy becomes a pale spiral, its arms glowing with star-forming regions, its center bright and crowded, its halo filled with ancient stars and dark matter. Around it drift smaller companion galaxies. Farther away, Andromeda shines as another great spiral, moving slowly closer across intergalactic night. Rise farther, the local group becomes a small cluster of points. Rise farther still, nearby groups and clusters appear. The Virgo cluster, rich with galaxies, lies beyond our small group. Superclusters and filaments begin to emerge. Galaxies are no longer individual jewels, but dust along glowing threads. Rise to hundreds of millions of light years. The cosmic web becomes visible. Long structures curve across darkness. Voids open like vast bubbles between them. Clusters shine at intersections where gravity has gathered matter over billions of years. Rise to billions of light years. The web continues, but on the larger scales the universe becomes smoother. No single direction seems special. No great edge appears. No center reveals itself. The cosmos looks statistically similar in every direction when averaged over enormous distances. Rise to the edge of the observable universe. There is no wall there, no shell of stars, no boundary where space ends. There is only the limit of ancient light, the farthest distance from which signals have had time to reach us. Beyond it, light may still be traveling or may never reach us because of expansion. The horizon surrounds us, and beyond the horizon, the unknown continues. This is the strange piece of cosmic scale. The universe is too large for us to hold directly, but not too large for us to understand in pieces. We understand light seconds, then light minutes, then light years, then galaxies, then clusters, then the observable horizon. Step by step, the mind climbs. The full scale never becomes ordinary, but it becomes approachable. A human lifetime is short compared with the universe, but the human mind can still place itself inside cosmic history. We can know that the calcium in our bones, the oxygen we breathe, the carbon in our cells, and the iron in our blood were made in stars and stellar explosions. We can know that Earth is one planet around one star in one galaxy among many. We can know that the light from distant galaxies has crossed space since before Earth had complex life, before the Sun existed, before the Milky Way had its present shape. To understand the size of the universe is also to understand our smallness. But smallness is not the same as meaninglessness. A telescope is small compared with a galaxy, but it can gather light from billions of years ago. A human brain is small compared with a planet, but it can calculate the age of the cosmos. A whisper is small compared with a star, but it can ask what the universe is. The size of the universe does not erase us, it places us. It tells us we are not the center of all things, but part of a vast unfolding reality. There is a kind of comfort in this. Earth is not large, but it is home. The sun is not unique, but it gives us day. The Milky Way is not alone, but it carries our star. The observable universe is not necessarily everything, but it is enough to fill every dream with distance. When we look up at night, we do not see the full universe. Our eyes see only a small fraction. City lights hide many stars. The atmosphere softens the view. The human eye cannot see most wavelengths of light. We cannot see radio waves, ultraviolet, X-rays, gamma rays, or microwaves without instruments. We cannot see dark matter directly. We cannot see beyond the cosmic horizon. And yet, even with the unaided eye, the night sky gives a hint. A few thousand stars, the pale band of the Milky Way, the wandering planets, the occasional meteor, the moon, the darkness behind everything. That darkness is not empty, it is full of distance. Every patch of sky, even one that looks blank, may contain galaxies too faint for the eye. Deep telescope images of tiny regions of sky reveal thousands of galaxies, each one containing billions of stars. The blankness is only the limit of our sight. The universe is not sparse in the way it appears. It is rich beyond ordinary seeing, but it is also mostly space. The distances between things are enormous. Stars are separated by light years. Galaxies are separated by hundreds of thousands, millions, or billions of light years. Even inside atoms, most of the volume is not solid in the everyday sense. Reality is full of structure and emptiness together. This combination repeats at every scale. Atoms are mostly space. Solar systems are mostly space. Galaxies are mostly space. The universe is mostly space. Yet from this spaciousness, matter gathers into stars, planets, oceans, and life. The size of the universe is therefore not only a matter of width, it is a matter of emptiness and gathering. Gravity gathers, expansion stretches, light travels, time reveals, matter clumps. Voids open, galaxies shine, horizons form. The universe is a balance between what comes together and what moves apart. On small scales, gravity can overcome expansion. Earth does not expand away from the sun. The solar system does not expand. The Milky Way does not expand internally because its gravity holds it together. The local group is gravitationally bound. But on very large scales, between distant galaxy groups and clusters, cosmic expansion dominates. This is why the universe can be expanding while local objects remain intact. The space between distant galaxies grows, but your room does not expand. Earth does not grow larger because the universe expands. Atoms do not stretch. The solar system does not drift apart from expansion. Bound systems remain bound. The expansion belongs to the largest scales. This matters for understanding size. The universe is not expanding into ordinary empty space around it. It is the scale of space itself that changes. Distances between unbound cosmic structures increase. The fabric of the universe stretches. This stretching also stretches light, producing redshift. The farther we look, the more expansion has affected the light. The more ancient the light, the more cosmic history it carries. At the edge of the observable universe, the ancient light of the cosmic microwave background has been stretched by the entire history of expansion. It began as hot light from a young universe. It arrives now as cold microwave radiation, faint but everywhere. That faint glow is one of the great treasures of science. It tells us the early universe was hot, dense, and smooth, but not perfectly smooth. Its tiny variations became the seeds of structure. Without those slight differences, gravity would have had no starting points for galaxies. A perfectly smooth universe might have remained almost featureless. But tiny irregularities grew slowly into the cosmic web. The largest structures we see today began as the smallest differences in the early universe. This means the size of the universe is connected to its beginning. The vast web of galaxies is not random decoration. It is the grown-up form of ancient fluctuations. When we map galaxies across billions of light years, we are seeing the later chapters of patterns already faintly present in the cosmic microwave background. The universe remembers. Its size is not only space, it is history stretched across space. Every distance is also a time. The moon, a little over 1 light second. The sun, just over 8 light minutes. Nearby stars, years. The Milky Way, thousands to 100,000 light years. Andromeda, millions. Distant galaxies, billions. The cosmic microwave background, almost the full age of the universe in light travel time, though the matter that emitted it is now much farther away. The observable universe, about 94 billion light years across today. These numbers are not just measurements. They are layers of memory. To look outward is to look backward. To measure distance is to measure time. The universe is a vast archive made of light, but the archive has limits. There are things we cannot see because their light has not reached us. There are things we may never see because expansion will prevent their light from ever arriving. There are early moments hidden behind the opacity of the young plasma. There may be regions so distant that they remain forever outside any possible observation. Science is powerful, but it is not omniscient. It works at the boundary between what can be measured and what can be inferred. That boundary is part of the beauty. The size of the universe humbles science itself. Not because science fails, but because it teaches us exactly where certainty ends. A weaker story would pretend to know everything. A stronger story says, this is what the evidence shows, and beyond it, the unknown remains. If by universe we mean the observable universe, the answer is roughly 94 billion light-years across. If by universe we mean everything that exists, the answer is that we do not know. It could be finite and far larger than we can see. It could be infinite. It could have a shape beyond direct visualization. It could contain regions forever hidden from us. The number we know is already enormous. The unknown beyond it may be larger still. This is not a failure of imagination. It is the beginning of wonder. Because the universe is large enough that even its observable part contains more galaxies than the mind can comfortably count. Each galaxy may hold billions of stars. Many stars may have planets. Some planets may have moons, oceans, atmospheres, storms, mountains, or perhaps life. Across the observable universe, there may be more worlds than grains of sand on all the beaches of Earth. And yet all of this may be only the visible patch. A sphere of light around one small planet, one observable bubble in a possibly much larger cosmos. There is a quiet feeling that comes from this thought. Not fear, not exactly. More like standing at the shore of an ocean at night, hearing waves you cannot see, knowing the water continues far beyond the moonlit edge. The observable universe is the moonlit water. The full universe is the dark ocean beyond. We do not know where it ends, or whether it ends. And still, we are able to know so much. We know that space expands. We know that galaxies recede. We know that the early universe left behind a microwave glow. We know that normal matter is only a small part of the cosmic contents. We know that dark matter shapes the web. We know that dark energy drives accelerated expansion. We know that stars made the elements that make planets and bodies. We know that Earth is young compared with the cosmos, but old enough to carry memory and rock, water, and life. We know that the universe is not static. It has a history. It changes. It evolves. It grows colder and larger with time. The size of the universe today is not the size it always was. In the earliest moments, the observable universe was compressed into a much hotter, denser state. Space expanded. Matter cooled. Particles formed. Atoms formed. Light escaped. Gravity gathered gas into stars and galaxies. Heavy elements were forged. Planets formed. Life appeared here and perhaps elsewhere. The universe became large through time. Its size is the result of its history. And its future size will be larger still. If dark energy continues as it appears to behave today, cosmic expansion will keep accelerating. Distant galaxies will slip farther beyond reach. Star formation will gradually decline as gas is used up or locked away. Existing stars will age. The universe will grow darker over immense timescales. The size of the universe is therefore also a future, a direction, a widening. Every second, the observable universe changes slightly. Light from new regions has more time to arrive, but accelerated expansion also places limits on what will ever be reachable. The horizon is not a simple fixed wall. Cosmology is filled with different kinds of horizons, each describing a different limit. What we can see now, what we could ever see, what we could ever influence, what could ever influence us. The universe is not only large, It is dynamic. Its size depends on time, observation, and definition. This is why the simple question becomes deep. How big is the universe? Do we mean what we can see? What exists now? What light has reached us? What light will ever reach us? What we could ever travel to? What we could ever affect? Each question has a different answer. The observable universe is not the same as the reachable universe. There are galaxies we can observe today whose current regions are already beyond any possible contact. We see their ancient light, but we could never send a signal that reaches them now if expansion continues as expected. Seeing is not the same as reaching. That is another lonely and beautiful truth. Astronomy is full of ancient arrivals. Light comes to us from places we cannot visit, from times we cannot return to, from galaxies whose present is beyond our touch. The universe gives us vision without access, memory without contact, a sky full of messages from unreachable places, and still, that is enough to learn. A photon can cross billions of years and end inside a telescope detector carrying information about a star, a galaxy, a cluster, or the early universe. Light is the messenger of scale. Without it, the distant universe would remain dark to us. With it, we can map the past. Every telescope is a time machine, not because it travels through time, but because light takes time to arrive. The larger the universe becomes in our understanding, the more time and space merge in our imagination. A galaxy, 10 billion light-years away, is not only distant, it is ancient in our view. The cosmic microwave background is not only far, it is early. The edge of the observable universe is not only a place, it is a time horizon. The universe surrounds us in layers of age. Nearby stars show recent history. Distant galaxies show youth. The microwave background shows infancy. The unobservable beyond remains hidden. This layered view gives the universe depth in a way ordinary maps cannot. A map of Earth shows places as they are at roughly the same time. A map of the universe shows different times at once. The farther out you look, the farther back you see. Cosmic distance is also cosmic memory. And because the universe is expanding, the distances we assign are not always the same kind of distance. There is light travel time, telling us how long the light has been moving. There is comoving distance, describing how far away the source is now in the expanding universe. There is angular diameter distance, luminosity distance, and other measures used by cosmologists, depending on the question. This may sound technical, but the reason is simple. In an expanding universe, distance is not one simple thing. The universe changes while light crosses it. A galaxy's light may travel for 13 billion years, while the galaxy's present distance is much greater. Its light may be stretched, its brightness changed. Its apparent size affected by cosmic geometry. To measure the universe, scientists must be precise about what kind of distance they mean. This precision keeps the mystery honest. It prevents simple misunderstandings. It allows us to say with care that the observable universe is about 94 billion light-years across today, even though the universe is only about 13.8 billion years old. The number sounds impossible until expansion is understood. Then it becomes one of the most beautiful facts in cosmology. The universe is old, light is fast, space has stretched. The horizon is farther than light travel time alone would suggest. There is a calm grandeur in that. Imagine holding a small globe of Earth in your hands. Then imagine the moon, 30 Earth-widths away. Then the sun, hundreds of times farther still. Then Neptune, thousands of times beyond Earth's distance from the sun. Then the nearest stars, so far that the solar system becomes a tiny point. Then the Milky Way, 100,000 light-years across. Then Andromeda, millions of light-years away. Then clusters, then filaments. then the cosmic web, then the microwave background surrounding all directions. Then the observable universe, a sphere 94 billion light-years across. Then the unknown beyond. At every step, the previous scale disappears into smallness. Earth becomes a point. The solar system becomes a point. The Milky Way becomes a point. Clusters become points. Even the observable universe may be only a point compared with the full cosmos, if the full cosmos is vastly larger or infinite. This repeated shrinking can feel overwhelming, but it can also feel peaceful. Our importance does not need to come from size. A seed is small compared with a forest, but it carries life. A neuron is small compared with a brain, but it participates in thought. A planet is small compared with the universe, but it can hold oceans, clouds, memory, and consciousness. A human life is short compared with cosmic time, but it can look up and understand billions of years. The universe is vast, and within it, awareness has appeared, at least here. That fact is not erased by scale. It is made more astonishing. The size of the universe gives context to everything. Every worry, every ambition, every city light, every quiet night, every question asked beside a window belongs to a small world in an immense cosmos. The scale can soften the mind. It can make the urgent feel less sharp. It can turn restlessness into wonder. Under the night sky, the universe does not hurry. Stars take millions or billions of years to live. Galaxies turn slowly. Light crosses space patiently. The cosmic microwave background has been traveling since the universe first became transparent. The largest structures grew over billions of years. Cosmic time is slow beyond human instinct. To think about the size of the universe is to slow down with it. A breath becomes enough. A moment becomes part of a larger unfolding. The mind can rest inside the scale. And perhaps this is why the universe is such a good subject for nighttime. Darkness is not only absence, it is depth. When the sky grows dark, the nearest distractions fade and the farthest light appears. The stars are always there in daytime too, but sunlight hides them. At night, the universe is not created, it is revealed. The same is true of thought. When the mind becomes quiet, larger questions can appear. How big is the universe? Where does it end? Does it end? What lies beyond what we can see? Will distant galaxies vanish from view? How can space expand? How can the observable universe be larger than 13.8 billion light-years in radius? How can we know so much from faint light? Each question opens another. The universe is not a single answer. It is a series of horizons. The first horizon is Earth's horizon, where land or sea curves away. The second is the horizon of the solar system, where the sun's family fades into interstellar space. The third is the horizon of our galaxy, beyond which the Milky Way becomes one island among many. The fourth is the horizon of galaxy clusters and the cosmic web. The fifth is the horizon of light itself, the observable universe. And beyond that is the horizon of knowledge, where measurement gives way to possibility. The final horizon may never be crossed, but it can still be approached with humility. The full universe may be infinite, and if it is, then every number we use for the observable universe is only a local fact. 94 billion light-years would be the width of our visible patch, not the width of all existence. There would be no farthest galaxy in the total sense, no final edge, no last star at the boundary of being. If the universe is finite, then it may still have no edge in the ordinary sense. Earth's surface is finite, but if you walk in one direction long enough, ignoring oceans and obstacles, you do not fall off an edge, you return. Space could, in principle, have a finite volume but no boundary, though in 3 dimensions and cosmic topology, the possibilities are far more difficult to picture. Finite does not necessarily mean edged. Infinite does not necessarily mean simple. The universe may be larger than imagination in either case. The truth remains unknown, and that is acceptable. Science does not demand that mystery vanish. It demands that we separate what we know from what we only wonder. It lets wonder remain, but gives it shape. We know the observable universe is vast. We know its scale because light has reached us from ancient sources. We know the cosmic microwave background marks the farthest light we can currently see. We know expansion has stretched distances. We know the universe has no known center or edge. We know the whole universe may be finite or infinite. We know we do not yet know its total size. These are not small achievements. They are among humanity's greatest acts of understanding. For most of human history, the universe was the sky above a flat horizon, the sun and moon, the wandering planets, and the fixed stars. Then Earth became a sphere. Then Earth became a planet. Then the sun became a star. Then the Milky Way became a galaxy. Then galaxies became countless. Then the universe became expanding. Then the cosmic microwave background revealed the early fire. Then dark matter and dark energy showed that most of the cosmos was hidden. At every stage, the universe grew. Not because it physically changed in that moment, but because human understanding widened. The size of the universe is also the story of our expanding perspective. We have moved from a human-sized cosmos to a planetary one, from a solar one to a galactic one, from a galactic one to a cosmological one. Each step removed us from the center, but gave us a larger truth. There is grace in being decentered. It means we belong to something far greater than ourselves, not as rulers, not as the middle, but as witnesses. Witnesses on a small planet, around a quiet star, in a spiral galaxy, inside an observable sphere of ancient light, surrounded by a universe whose full size remains unknown. The thought is almost too large, so we return gently to the beginning. Earth, night. A listener resting somewhere on the surface of a blue planet. Above you, the atmosphere thins into space. The moon circles. The planets move around the sun. The sun orbits the center of the Milky Way. The Milky Way moves within the local group. The local group flows within larger structures. Galaxies trace the cosmic web. The cosmic microwave background surrounds the sky. The observable universe extends tens of billions of light-years in every direction. And beyond it, the unknown continues. You do not need to hold all of it at once. No one can, not fully. You can simply let the scale open slowly. Light second, light minute, light year, galaxy, cluster, cosmic web, observable universe, unknown beyond. Each word is a step into a larger darkness. Each step is calm. The universe is immense, but it is not rushing you. It has been expanding for nearly 13.8 billion years. It has carried starlight across impossible distances. It has formed galaxies, planets, and minds slowly enough for wonder to arise. And here, for a short while, we can listen. We can imagine the moon's light crossing 1 second of space, the sun's light crossing 8 minutes, a nearby star's light crossing years, the Milky Way's starlight crossing thousands upon thousands of years, Andromeda's light crossing millions, distant galaxies crossing billions, the microwave background crossing almost the whole age of the cosmos, all of it arriving quietly, all of it entering telescopes, eyes, instruments, and thought. The size of the universe is not only out there, it becomes part of the mind that contemplates it. When we understand a distance even slightly, we make room inside ourselves for something vast, and perhaps that is enough for one night, not to solve every mystery, not to reach the final edge, not to know whether the whole universe is finite or infinite, but to rest with the truth that the observable cosmos is already almost unimaginably large, and that beyond it, Reality may continue farther than light, farther than sight, farther than certainty. The universe is not a room with a wall. It is an expanding ocean of space and time. We float within it on a small blue world. We look outward through ancient light. We measure what we can. We wonder beyond what we know. And in the quiet between those two things, knowledge and wonder, the size of the universe becomes not only a number, but a feeling. A feeling of depth, a feeling of distance, a feeling of humility, a feeling of peace beneath the stars. So as the night continues, let the thought of the universe become gentle. Let Earth be small but safe. Let the stars be distant but calm. Let the galaxies drift in the dark. Let the ancient light keep traveling. Let the cosmic horizon remain where it is, not as an ending, but as an invitation. Beyond what we can see, there may be more. Beyond what we know, there may be more. Beyond every horizon, another question waits. And for now, that is enough. The universe is vast. The observable part alone is wider than the mind can easily hold. The whole may be larger still, perhaps finite, perhaps infinite, perhaps shaped in a way we have not yet imagined. But here, beneath the quiet sky, we are part of it, made from its atoms, lit by its stars, carried by its expansion, surrounded by its ancient light, and held for one peaceful moment inside its immeasurable dark.